again, some of these, you can kind of just, we won't prove them, you kind of just copy them down. We'll kind of maybe refer to them later. Some of them may not make a whole lot of sense right now, but we'll use them later in the semester. So let phi be a group homomorphism. And let H equal the kernel of phi, and let A in G, let A be in G, then the set phi inverse of phi of A is equal to those values in G such that phi of X equals phi of A. And so again, if this is the kernel and these are the values in the inverse of this, or the values in G such that produce phi of A. And this turned out to be, this set is both the left and right coset. Of H. So in other words, it's both AH and HA. A group homomorphism B to G prime says a group homomorphism is a one-to-one map if and only if the kernel of phi is equal to the identity. Homomorphism. G prime, that is one-to-one and onto is called an isomorphism. And then two groups G and G prime are called isomorphic. If there exists some isomorphism that maps G to G prime. So main things, so of all the things said here, I suppose the most important thing is just to understand, first of all, this definition. If you have a homomorphism from one group to another, and it's one-to-one and onto, then it's called an isomorphism. Then two groups are called isomorphic if there's an isomorphism between them. And let's see. And so to show, and again, a lot of this stuff is for the future, but to show that something's an isomorphism, you go through these steps. Step one, show phi is a homomorphism. Step two, show that the kernel phi is equal to the identity. Or now I'll just put in parentheses here, or show in another way that phi is one-to-one. And step three, show phi maps G onto G prime. So again, I use a lot of this later, but this is a way to show something's an isomorphism. Again, show it's a homomorphism. Show it's one-to-one. However you do it, it can be shown this way, that the kernel phi is just the identity, and you have to show that phi maps G onto. It's an onto map to G prime. And then another definition is for a normal subgroup. Subgroup H of a group G is normal if its left coset and right cosets are the same. That is, if GH equals HG for all G in the group. So in other words, if all of its left and right cosets, for every possible member of G, if they're equal, then it's called normal. the group does not have to be a billion for this to be true, though if it is a billion, all of these the subgroups will be normal, because remember, billion means that you can commute all the members. So therefore, if all the members commute, that's always going to be true. Suppose G and G prime are isomorphic, then A, G, if they're isomorphic, then the order of G is going to be equal to the order of G prime, which kind of makes us, again, we haven't looked at a lot of details, kind of makes sense. You know, if something is like 1-to-1 and onto, well, first of all, the fact it's 1-to-1 means there's going to be a, 1-to-1 correspondence. So you would expect the number of elements in the groups to be the same. And B, G is abelian. If and only if G prime is abelian. And C, G is cyclic. If and only if G prime is cyclic. And another proposition. Let G be generated by A, be a cyclic group. Then A, if the order of G is infinite, then G is isomorphic to the integers, of course. And so just take a look at that for a minute. So this is saying if G is a cyclic group, it's generated by some element A, it's a cyclic group. And if it happens to be infinite, then it's going to be isomorphic to the integers. In other words, there's going to be like a 1-to-1 onto map to the integers. Now, keep in mind, of course, when you think of a group that's infinite, you might think of, like, say, the real numbers. That's an infinite group, but it wouldn't qualify here because you can't generate the real numbers by like a single element. And so therefore this is limited to a cyclic group, one where you can actually generate it by repeatedly adding or multiplying a single element. And so there's really going to be discrete values for this group. And so you can always find an isomorphism between a group like that and the integers. And then if another related one is if G, again, it's a cyclic group, and let's say its order is n. So again, it's like a finite group. Again, it's a cyclic group. Then G is isomorphic to Zn. You know, the Zn we're familiar with, that'll be like 0, 1, 2 up to n minus 1.